In this video, we're going to be going over logarithmic functions and how to graph them. So these will be graphs in the form of y is equal to log a, where a is a number, and then x. Then obviously dilations, translations, and reflections may change around the form, so it may end up looking something like this. However, the base function looks like this, and then you can apply the different transformations which we'll go over to get something that may look like this, and then how you graph that. So firstly, what does a log function look like, the standard log function? So talking about here, y is equal to log a to the x. Now a can be any number, however, apart from changing some of the steepness at points, the general shape stays the same. So we'll graph y is equal to log 10x first. Well, the first thing is that if you remember that log y is equal to log 10x is effectively saying 10 to the y is equal to x. Now we know that 10 to the y, or any number to the power of another number, will always have to be greater than 0. So that means that has to be greater than 0. So therefore we know that x has to be greater than 0, and y can be any real number. Then when x is really, really small, to achieve this, y has to be very, very negative. So when x is small, y has to be negative, something like this. Then when x is greater than 1, y has to be equal to 0. That's because any 10 to the 0 or any number to the 0 will equal 1. So that means x is equal to 1 when y is equal to 0. And that gives us the x-intercept. So x-intercept here is 1, 0. Then when x is greater than 1, y has to be a bigger number. But when y is equal to, let's say, 3, that's going to be 10 to the 3. So x will equal 10,000. So a very large number. Like 10 to 3, so 10 times 10 is 100. 100 times 10 is 1,000. So not 10,000, 1,000. But as you can see, 1,000 is going to be a very long way. Y is equal to 3 here. So the graph is going to curve like this. So this is what the log function looks like. Y is equal to log 10x. Now let's say instead we had y is equal to log e to the x. Now e is approximately 2.7, so it's going to be not as steep as this y is equal to log 10x. That's because up here, at every x value, you're going to need a slightly bigger y value. So it's going to look something like this. And then to achieve this x value, you're going to need a greater y value. That's because you have the 1 on 10y, so it's going to go down here. However, it does have the same shape, and it also does intercept through this 1, 0. As you can see down here, though, the graph starts to look like it approaches a value. Up here, just it keeps on going and starts to approach. Doesn't really approach a specific number, but here you can see that x has become smaller and smaller and smaller. Y approaches negative infinity. So when x approaches 0, then y approaches negative infinity. So along here, we're going to have an asymptote. So no matter what base you're looking at for the log, you are going to have this asymptote along the y-axis here. So you put that in, state its equation, so x is equal to 0, and then you have that. But note there's only one asymptote, there's not an asymptote horizontally, unless you are doing unless there's been some transformations. But even then, there actually still won't be a horizontal. Yeah, so there's always going to be a vertical, but there'll never be a horizontal for the logarithmic function. So beginning with some dilations. So we have a general shape here. And we know that that goes to the point here, 0, 1. That's y is equal to log e to the x. So we'll just take log e to the x, but it could be any other ones. And that's just like a general shape, it doesn't matter too much. And then let's say from the x-axis we're replacing y with y on k. Then we're going to get y on k is equal to log e x. Therefore y is equal to k log e x. So let's say we use a function when, let's say k is equal to 1. Oh, k is equal to 1, this is this one here. What about k is equal to 2? That means we'll get y is equal to 2 times log e x. That means that every x value, y is going to be a larger number. So that this graph here is already pretty steep. So I'll just bring it down a bit. Obviously, not to scale, but it'll look something more like that. So then when you have y is equal to 2 log x, it's going to be up here. So it's going to be greater at every x value. And then when y is negative, it's going to be an even more negative value. So at every x value here, it's going to be more negative. So it's going to look like that. So that here is y is equal to 2 log ex. And then the other way around, you can see it's going to look like this when that is y is equal to a half log ex. So then dilating from the y-axis, we have to replace x with x on k. This gives us y is equal to log e x on k. So how does this affect the graph? Well, we have the original here. I'll just note that this point here is going to be 0, 1. Then if k is equal to 2, we're going to get y is equal to log e k to the k over 2. Now this point here is 0, 1. So that's because log e, the reason for this one here is because when you have log e to the 1, that's equal to 0. However, now when you sub in x is equal to 1, you're going to get log e a half, which is not going to equal 0. So now this point here is going to be when x is equal to 2. And that's because when x is equal to 2, this whole function here will equal 1. So when x is equal to 2, then we're going to get log e1, and that will equal 0. So graphing this, we're now going to have this point here, which is going to be 0, 2. Then it will come down like this. It will start to approach the other graph, and then it'll be like that. That is y is equal to log e x on 2. So the difference between dilation from the y-axis and the x-axis is that with the base form, when you dilate it from the y-axis, you are changing the x-intercept. And then conversely, when you let k equal a half or something similar, then you're going to change a function and you're going to get y is equal to log e 2x. And for 2x to equal 1, we need x to equal a half. So when x is equal to a half, we get log e1, which equals 0. So that's going to be the x-intercept. So this point here will be a half 0. And then it will be the similar shape as we had before. But now you're going to have y is equal to log e 2x. So reflections. Reflections you can see pretty easily whenever you graph it. So if you have that thing and we're doing it in the x-axis, then you're reflecting it in the x. So it's going to look like this. And at this point, that's going to be, if it's a standard graph, it's going to be 0, 1, 1, 0. So reflecting the x-axis, you can see that. So what happens to the equation? Well, when you're reflecting the x, you're replacing y with negative y. So that means this equation here will go from y is equal to log ex to y is equal to negative log ex. And you can see the change there. The main thing you have to be careful of is when there's translations and translations or dilations beforehand, and this may slightly change the reflection. But just look at the x-axis, make sure you reflect it, change y with negative y, and see what the new equation will be. So what about if we're now reflecting in the y-axis? So we have this standard here, and also the asymptote has remained the same here at x is equal to 0. And that was the same before when we looked at dilations. There's still the asymptote there. I just didn't draw it in. However, if you were drawing the graph, you would have to put the asymptote, but it is unchanging in both these dilations. So with the reflections, we're now reflecting in the y-axis. So that means we reflecting here. The graph is going to look like this. As you can see, it's a reflection in the y-axis. So this point here will now be -1, 0, or if that was 1, 0. However, if there was dilations and that was, let's say, 2, 0, then this would become -2, 0. The asymptote stays the same here at x is equal to 0. And that's because even though it's on the other side now, it's still approaching negative infinity, but you're approaching 0 at different points, but you're still approaching the same value. So with the reflections, just graph them out. They don't change the asymptote. Then just look at the x-intercept, see how it changes, and then look at the equation. So if it's in the y-axis, you're replacing x with -x, and this means here, this graph will be y is equal to log e -x. Just be careful though, if it was translated and let's say the asymptote was here at x is equal to 1, so it's at x is equal to 1, and you have the equation here, then when you reflect it, the equation then becomes, the asymptote then becomes x equals -1. You can see that, but when x is equal to 0, plus or minus 0 still gives you 0, but when the asymptote is non-zero, then have to be careful that you will also have to reflect the asymptote. So when it's exactly on the axis, it doesn't reflect, but when it's on either side, it will reflect. So going on to translations. So translations in the y direction, that's when you're replacing y with y minus k, which will give us y is equal to log e x plus k. Now this, if we have the original graph here, this is going to shift it up or down, and thus shift the x-intercept, but the graph will remain the same. So if it's like plus, let's say plus 2, so log e x plus 2, then when y is equal to 0, we're going to get 0 is equal to log e x plus 2, so -2 to the other side, and then we can solve for that, take e to the both, and then x is equal to e to the -2. So we're going to get that graph here, and the way I did that is I took e, put both sides to the power of e, so e to the power of -2, e to the power of log ex, and the e log ex cancelled. So this point here would be e to the -2, 0, and then we'll have the same graph here, but you've just shifted it up. So every point here is going to be up 2 values. Then if you minus, it would be a similar thing, but you'd have this graph here, and then -2. The main thing is you still do have to write the x-axis, and the asymptote still remains the same at x is equal to 0. But the main thing is you still have to write the x-intercept in, and you just solve for what I did here, where you let y equal 0 for the x-axis intercept, and then you minus a 2. If you get an equation like this, then you want to get rid of the log ex. You can do that by going e to the -2 is equal to e to the log ex. The e's cancel, and we get x is equal to e to the -2, which is equal to 1 over e to the 2, which is a pretty small number. If you remember, e is about 2.7, so this e squared is going to be between 4 and 9. So what about dilations from the x direction? So this is when we're replacing x with x minus k. So we're going to get log e x minus k, and then y is equal to this. So the main thing about this translation is you are changing the asymptote. So this point here is going to be 1, 0. However, when you have y is equal to log e x minus k, then the asymptote will change. So previously you had the asymptote here at x is equal to 0. But now we have to think, when, let's say k is equal to 3, we'll get log e x minus 3. Now when x is equal to 3, then log e 0. But log e 0 doesn't exist. Now when we have let x is equal to 4, we find that we have log e 1, which is equal to 0. So now we've shifted it 3 across, so effectively k is equal to 3, so we're plussing 3, then we're going to shift the asymptote here. And now this point here will be x is equal to 3. This point here will now be 4, 0, and we'll get the exact same graph, but it's now shifted 4 across. And the asymptote also does shift. We can see this. When x is equal to 3, log e is 0. This is undefined. When x is equal to, let's say, 3.001, then we're going to get log e a very small number, but not 0. And to achieve this small number, y is going to have to be a very negative number. So you can see that this, what happened here before when x is equal to 0, now happens again, but when x is equal to 3. The easiest way to think about it is that everything shifts across 3, including the asymptote, and you can see that from the equation because x can't even equal 2, because log e negative 1 is not defined.